Cool. So we've got a bit to get through today. We're probably not going to get through all of it. That's okay. We have some wiggle room built into this class. Want to just touch on a couple things. This iteration, I've been sort of deliberately going a little slower pace through everything. I know it does feel like a fast pace. I'm just saying this because we're just going to start reiterating, since this course works, I think it's safe to say, quite a bit differently than courses that you may be familiar with. We're just going to kind of start reiterating that. So the idea is we want to be able to cover this material kind of as quickly as we reasonably can, and we're aiming at a wide audience of backgrounds, of skill set. Some people are coming from technical backgrounds, some people have coding experience, and some don't. Some are coming from humanities backgrounds or other backgrounds that don't involve technical work or coding in particular. So that's fine. Of course, everybody's welcome. I definitely consider it a personal goal of mine to make it available to everybody that it can be available to. And yeah, so don't hesitate, even though we move kind of fast. If a concept doesn't land the first time, it's not the only time that it's going to be brought up. In my experience, things just have to be repeated, right? I don't think I've met anybody, or at least hardly anybody, who gets all these concepts on the first try. So we have there's an idea that some of you may be familiar with in pedagogy about spaced repetition, where we introduce an idea kind of at a glance and then come back to it and cover it a little deeper the next time, and then cover it a little deeper the next time. So the ideas cycle through, and yeah, that's part of the model. And you're welcome to, since we move quickly and since we cover kind of a lot of material, you're welcome to reach out. Please DM me if you're just having a hard time with something. It's totally fine to just say hey, I'm having a hard time with this. I don't even necessarily know what to ask, but can I get some help? And we'll go from there. If you're stuck on something and learn, feel free to just shoot it over to me. If you're working on something for more than 10 or 20 minutes, it's probably time to reach out for help in some way. So again, your resources are the Slack channels. That's this channel. You're welcome. I know I'm kind of strict about getting everybody to post in the thread during class time, but outside of class time, you're welcome to post in the channel, and then just keep things threaded just to keep it clean as much as possible. You're also welcome to use the basic prep Slack channel as well. That's open for everybody. That's always a pretty active channel. You're welcome to come to study halls and ask questions there. I just had a study hall today. We have those every Monday, Wednesday, and Friday. You can look at the study hall channel for more details on that. And then you're welcome to reach out to us. You're welcome to reach out to the instructors. Tovio or I are both available to meet one-on-one, as well as the other staff here is willing and able to meet one-on-one with folks. Cool. So we've got, like I said, we've got quite a lot to get through today. Last time we didn't get to go through sets, so I want to go through those really quick. We'll just cap this off. Fortunately, there's not too much going on with sets. Let's just do a quick kind of high-level overview. Oh, we don't need this anymore. Of what sets are. So sets are unordered, meaning that the order in which elements go into the set is not preserved like it is with a list, right? So if I have an empty list and then I append the number 70 and then the number 50 and then the number 80, that list is going to contain 70, 50, and 80 in that order. Sets have no such ordering. Sometimes you'll like print off a set, and you might print it off a few times, run your program, and find that it does return in the same order every time. Often the most efficient way for Python to present the information happens to coincide with the order things went in. Probably because it's reading bytes in a certain order in your memory, and the order that they were created in is likely to matter in that in terms of just optimizing the process of collecting the pieces of the set and printing it out, right? Or dealing with it in some other way. But it's not guaranteed. So this is why this is actually a good example if you want to know the difference between something that's arbitrary and something that's random, right? So something that's arbitrary, the order in this case is arbitrary. It's not random because it doesn't come out in a different order every time necessarily, right? It may or may not. So you basically can't count on the order. Since it doesn't have an order, sets also don't have indices, because it would be pretty meaningless to ask for the third element if you ask for the third element 10 times and you got a different answer every time, or you got a different answer like 1 out of 10 times. That'd kind of even be worse, right? Some consistency would be worse than none at all. So for that reason, sets just don't have indices. So they are not useful in the ways that a list or, say, a tuple is useful. So lists and tuples are both ordered types. They're collections of arbitrary objects. And we can make a collection of objects and then retrieve those objects out as we need them. Or deal with the collection as a whole in various ways, like looping through it or doing transforms on it, whatever. Sets are not useful for that. Sets are useful for doing set operations, which we're going to look at in a second. So that's what's meant by unordered. If you want an analogy, think about like an unordered type, and I've probably given this analogy before, but just to reiterate, an unordered type would be like a jar of, say, jelly beans, or a jar of anything, really. If you had a big jar of jelly beans, it wouldn't really make sense to say like, hey, hand me the 43rd jelly bean in that jar, because you don't know, where do you start? Which is the first jelly beans? The jelly bean doesn't have a number associated with it. But if you put a bunch of items in a row on a shelf or something, it'd be pretty easy to say. It'd be probably pretty understandable if I said like, hey, hand me the third item on that shelf. You'd probably start at the left and then count 1, 2, 3, in a one-based indexing pattern. But that'd be an example of ordering, right? Cool. So sets are mutable. Remember, lists are mutable. Tuples are immutable. Mutability just means that the object itself is capable of changing its value. In other words, there are tools, usually methods. Sometimes there are other things, like lists support item assignment. We can reassign an item at a given value, at a given position in a list. That's a mutable operation that isn't associated with a method, but usually mutability happens via built-in methods into via the types built-in methods. So there are several methods for sets that allow us to add and remove elements from them. Sets only contain unique elements. So what's meant by this is, if I have a list, I could have a list of 4, 5, 4, 7, 4, and I mean, no surprises here. List has what I put in it, and it has multiples. It has these duplicated values, and that's fine. That's totally fine in a list. In a set, and what I usually do is I just I keep my data in lists or tuples and then I usually will just cast it as a set as I need. If I cast this list as a set, notice that the duplicates get removed. And if I were, in fact, to go through and remove the duplicates from this list, I'd end up with the same thing. And this is a scenario I've recently discovered. A set of integers, in my experience, will always print out in the same order. But don't go thinking that sets are ordered types. It'd be sort of dangerous to think about them as ordered because they're not really. So, or let's just do a hello B. So I'm going to make a set of strings, and we're going to see this is going to come out in a different order. Oops, every time. Yeah, so anyways, that's coming out in a different order every time, right? So, what the heck? Okay. So, we've covered unordered, mutable, and unique elements. We recommend declaring a set with the set constructor function like this. So usually if I'm just going to make an empty set, I'll sum set equals set like that, and then I'll print it off. Set. If you want to make a set accumulator, you can start a set accumulator, an empty set like this, and then do your loop. And then when it comes time to append, instead of append, you use dot add. So I'll say sum set dot add, and then let's just do that. So add is the way of adding an element into the set. Cool. Okay. So, like I said, their application, the important role that sets play is for set methods. Oops, I'm on the wrong one. Here we go. Also removing duplicates. I kind of gave an example of this before. In certain cases where you want to remove duplicates, it's useful, if you have a list, it's useful to just cast it as a set arbitrarily. And that will give you a set of the elements, and the duplicates will be removed. Sorry, 1 second here. Let me, I'm going to just run and turn my light on really quick. Okay. So removing duplicates. This is one of the uses for sets. Although often by casting something as a set, let's say you have a list, you want to quickly remove the duplicates, ask yourself if the order of the elements in the list matters. And if it does, you might want to look at a different way of removing duplicates. You could write a function probably pretty easily that would take in a list and then give you back another list without duplicates in it that would still do something like preserve the order. So these, union, intersection, and difference, these are the set operations that I keep talking about. Actually, we'll just do this. Union, intersection, and difference. Okay. So the union and the intersection methods in sets are similar to their mathematical analogs. The union is the set of all the elements in two sets. So if I have set 1 equals set of, and I'm going to cast a tuple as a set, let's say 3, 5, 4, and we'll do set 2 equals 3, 7, 8. Okay. Let's just do this. Okay, so this is set 1 and set 2. If I want the union, I can say set1 dot union set 2, like this. Set1 dot union set 2, and it doesn't matter which order they go in. I'm still going to get the same thing. So notice, let's make this even simpler. 1, 2, 3, and we'll do 3, 4, 5, right? So set 1 and set 2, and maybe I even want to do, let's do this. Yeah, this is better. So set 1 and set 2 each have some elements in common with each other and some elements that are unique to them. So if I do the union, I'm going to get all of the elements that are in set 1 and all the elements that are in set 2 returned as another set. So notice both set 1 and set 2 contain 3 and 4, but of course, since we can't have duplicates in a set, the elements have to be unique. 3 and 4 only show up once in the union of set 1 and set 2. And just to drive this home, order doesn't matter. Set 1, set 2, set 2, set 1, not important. Intersection. So intersection is everything that set 1 and set 2 have in common, right? So this is going to be 3 and 4. So it's everything that's in set 1 that is also in set 2. 3 and 4, right? And again, this operation also doesn't depend on the order, right? So we can do set 1, set 2, intersection set 2, or set 2, intersection set 1, and that's going to be the same. Lastly, we have difference. Now, if you notice, here, I'll comment these out just so we can hone in on this. If you notice, the order changes the result here, right? So set 1 dot difference set 2 is all of the elements that are in set 1 that are not in set 2. So set 1 dot difference whatever is necessarily a subset or equal to, or an equal set to set 1. Likewise, set 2 dot difference set 1 is necessarily subset or equal to set 2. So if we look, set 1 difference set 2, set 1 has 1 and 2, and those are the two elements that set 2 does not have, that set 1 does have, right? So set 1 has 1 and 2, and set 2 does not have those. And likewise, we get set 5 and 6 for set 2 dot difference set 1. You can also think of difference as subtraction, right? So if we subtract what is common, then we end up with what's different, right? So set 1, all the elements in set 1 minus the elements that are in set 2, right? So if it's in set 1 and set 2, then it gets removed on the output. That's the difference. So fortunately, we can just use the subtraction operator like this, and makes it kind of nice. And I'll usually use minus like this if I do difference, but cool. So that's what sets are useful for: union, intersection, and difference. And if we come in, let's start an IPython session real quick. If we do dir of set, you're going to see we actually have a few methods in here. I covered add. Since sets are mutable, they have a copy method. If you're familiar with why to use a copy method with a list, then it's the same with sets. So basically, if you're passing a mutable object to a function, you don't want the function to be able to have agency to like change that object itself. You probably want to make a copy and then alter the copy, and then that way you don't alter the input into the function itself. So it just kind of keeps things safe. It means that you're not going to change something. You can just get something that has the same values and then alter that copy, right? So clear works the same way as it would for a list. It just removes all the elements. We covered, so I mean, you basically know what those do. Difference we just covered. Intersection, oops, I can't. And union. Pop takes an element and removes it from the set. So if I wanted to like remove this 5 from set 2, I could say set 2 dot pop 5. Type, oh, pop take, oh wow, okay, sorry, I forget this. Pop takes no arguments for sets, so it just essentially removes an arbitrary value. So in this case, it removed the 3. So yeah, anyways, remove, I think it's remove that takes the element. So if I wanted to remove the 5, yeah. So I was thinking about remove. But those basically, I mean, they're similar to the way they would work in a list. And then there's some other ones in here. We're not going to go over the other remaining methods in there. If you want to play around with them, you can. But the important ones to remember are, I'll say, add, copy, union, intersection, and difference. All right, awesome. The rest of today is going to be basically broken into breakouts. It's going to be the big meat of today. Okay. 1 second here. Let me get... Here's the breakout. And I'll put 3 minutes on the clock and you can work through that. Go ahead and paste in your answers in to learn. Excuse me, I mean into Slack. I don't know why I said learn. All right, we got another one. We got 4 minutes on this one. Put in your answers. Yeah, there we go. Feel free to put in your answers as soon as you've got them. So if you're done, you don't have to wait for me to tell you. Cool, that's time. Go ahead and put in your answers. I'm gonna throw in. Oh, what's this? The picture of the answers there for your reference. I'll get the screen share going again. All right. We got a question here. Can I explain specifically what's going on with split list? Let's see. Lower, replace, split. Where's, if the context of this is obvious, I am missing out somewhere. I'm sorry. It's right there, isn't it? Gosh. Yeah, let me find that. That's in this one. I'm looking in the wrong document. Apologies. So these are just meant to clean these, and this is actually going to turn it into a list at the end, a list of words. So if we cast this string as a set, which we could do, why is this called stir? Oh, that's silly. This should be. Wait. Oh, I copied the same one twice. Gosh. Okay. Let's try this again. These should probably be called set1 and set2. We could cast this string as a set. I'll just print set2 here. But we get a set of all the characters. So we want to clean it first. So we'll dot lower everything. Dot lower returns a string with all the capital letters lowercase. And if we do this, I mean, somewhere in here, I mean, if you want to go track down that uppercase C, but, and then dot replace is gonna just get rid of a character that we don't want. So we don't want periods. We're gonna replace them with nothing, with an empty string. Empty string is not a string with a space in it. It's a string with nothing in it. And then we're going to, so dot replace returns a string with all the elements that you wanted to replace, replaced with what you wanted to replace them with. In this case, we wanted to replace dot with nothing. So this returns a string without dots. Since that returns a string, we can chain another string method on it, and we can do dot split. And we want to split on spaces, which we don't really need to tell it to split on spaces. It'll just split on spaces if we don't say otherwise. So that'll split, and that'll give us a list of words because it's splitting on spaces. Split returns that list, and then we cast that list as a set, and that's why we get a set of words. Cool. All right. Hopefully that helps. It's funny. I had this question earlier, essentially this question earlier today in study hall. If you want, you could look at today's study hall if you want more of a in depth on that particular thing about chaining methods, and that might give you some more insight as well. Cool. All right. Let's see here. Let me retrace where it was. Okay. So tuple reviews. So real quick here, I forgot to do the overview that I've been doing, which let's just do that really fast. So basic, problem solving categories, basic problem solving tools in Python. We want to understand how the language evaluates. We want to understand what the data types we have are. We want to know how to abstract. We want to know how to do control flow. And we want to know how to iterate. So evaluation, these are just kind of language details, things like, what constitutes an expression in Python, and the type system, and how the document is executed. I've been kind of leaving that one out lately because we kind of went over that stuff in the first day. The challenge is really in data types. Like that's where we've been spending the last few classes, is in learning different types, learning what tools and resources we have for dealing with the types. Abstraction is variables. We talked about variables. We talked about functions. Control flow. That's going to be if, elif, else. Iteration. Iteration is going to be for loops and while loops. Today we're going to actually talk about, so these are the two major ones. These are the two big ones that we want you to use. These will do all your heavy lifting. There are some other ones that technically are redundant to these. While loops, just for context, can do everything a for loop can do, although they leave more to you to manage and deal with as the programmer. So they're a little harder to deal with. So for loops make the problems that they can solve easier to deal with. We also talked about some secondary iterators. We talked about map. Today we're also going to talk about comprehensions. List and dictionary comprehensions. These are technically redundant. So you will see them like out in the wild, so that's why we teach them. And ultimately, like in the long run, you will want to know these tools. You will want to know how to use them because they do have their own applications. They can make for really elegant code and potentially really optimized code in certain circumstances. But for now, like this class is focused on problem solving, just getting to working solutions. For and while loops are going to do that. There's nothing map and comprehensions is capable of in terms of problem solving that isn't covered by for and while. Cool. So the material that we've been covering, that we're going to cover today, is all centered around data types. Sets, tuples, and dictionaries. Let's do this. Whoops. And we'll put sets down here at the bottom. So I'll put tuples up here with the immutable types. So int and float. We also have string, bool. Let's put bool up there where it belongs. And none. We've talked about lists, and sets go with lists and dictionaries like that. So, and that's all the major built-in types that we're actually going to cover, that we expect you to like have a handle on. Cool. Okay. So that being said, let's do some tuple reviews. So tuples are ordered, meaning they have an index. The order that the elements go in is the order that they're preserved in. The order is significant and it matters. So they're ordered collections like lists and strings. Tuples are very similar to lists with two key differences. They are immutable. I mean, really, this is just trivia. It's a visual difference. It's not like a logical or a meaningful difference. Tuples are delimited with parentheses. Like I said, it's just a visual difference. It's not really same kind of difference. So I would say there's one really important difference, which is that they are immutable. So you can think about it like if you wanted a list, but you wanted an immutable version of a list, you'd end up with a tuple. We can index into a tuple in the same way that we could with a list. We can also slice. We can concatenate tuples. Tuples only have two methods associated with them: count and index. Functions return tuples when returning more than one item. So this is kind of a funny thing. Sometimes it's kind of a matter of how certain things are phrased. Sometimes you'll hear people talk about a function having multiple returns. A function in Python returns multiple things. People will talk about things in those terms, and really what they're saying is it returns a tuple. So if I write a function def sum function takes in x and y, and if I return x squared and y squared, I'm returning these two values, but it returns as a tuple, right? So if I print this off, some function takes in 4 and 7. So notice 16 and 49 are 4 and 7 squared respectively, and it comes out as a tuple. So just remember, when you hear somebody talking about a function having multiple returns, it's a way of making it sound fancy when you say, it just returns a tuple. Okay. So the thing about only having two methods, let's come back up here again. Let's do dir of list. And actually, I'll open another terminal session here. Put this one here. So here's the directory for lists. And let's do dir of tuple. Okay. So we can see them side by side like this. If I look through the list and I find all of the methods that are immutable and I disregard them, I end up with only count and index left over, right? So append, clear, copy, extend, insert, pop, remove, reverse, sort are all mutable methods. They all cause a mutation in the list. And if I remove all of those, I'm just left with count and index. So, and that's what tuples have. So they are very much just immutable lists. Uh, Dictionaries. Now, dictionaries have a pretty similar job potentially to lists and tuples in that we can store elements in them and retrieve them later. There's a lot of times where you solve a problem using a list or a tuple. You could use a dictionary. A lot of dictionary problems you can use a list or a tuple. Um, you might have to be a little creative and like reworking it because it's gonna, your output type is gonna look different, but there's enough similarities that with a bit of a stretch you can apply one to where you would use the others. Often, not always, but often. So dictionaries contain, instead of containing elements that have an index where the index is automatically given, dictionaries have values with a key associated with that value, and the key is something that you have to manage, in that you have to supply something that becomes the key for the dictionary. You essentially have to to explicitly supply the key. So the key is to value in dictionaries as index is to element in lists. So if you wanted to describe a list as lists contain index element pairs, right? You could, this is a bit of a stretch of the analogy here, but you could think about it like that, right? Lists and tuples do contain pairs of indices and elements, but we don't think about adding the indices. We don't think about managing those indices. We just add in elements, and the element automatically has an index based on its position wherever we put it, wherever it's left over in that collection. Whereas with a dictionary, you just have to remember you have to like kind of manage two things a little bit. So they can feel like they have a lot of moving parts, and I think it's safe to say that they're the most complicated type that we've covered thus far. They're the most complicated built-in type in Python, but they're not terribly complicated. They're very manageable and very learnable. So they contain key value pairs in a mutable, unordered collection. So they are mutable like lists and sets, and they are unordered like sets. There are certain circumstances and there's certain problems in Learn where there's certain circumstances, certain problems in Learn that sort of rely on certain cases where a dictionary will kind of retain an order. In general, don't think of them as ordered. That's just not it's not a useful way of thinking about dictionaries. Even though the ordering is fairly consistent and fairly quite often, in fact, usually, you'll see the elements presented or processed in the way that in the order in which they were put in. But for the times when that's not the case, if you were to go about thinking about dictionaries as ordered, that would potentially bite you, come back around to bite you in the end. Cool. So keys like elements and sets, and oh, I think I forgot to mention this. This can be said about elements and sets as well. Keys must be immutable and unique. So just like sets contain unique values, we can't have two of the same key. And keys have to be an immutable type. So they can be any type. They can be a string or an integer or Boolean, but they have to be immutable. And this is one of the reasons I always kind of make this split here when I do the overview. You might think, oh, this is just kind of like an arbitrary grouping where I make a group of the immutable types and I make a group of the mutable types, and it's just like, you could group these. Why not group all the collection types together, or like this, or why not group all the weird types together and all the number types and then all the collection types, but this ordering is significant. It's pretty useful to have a very clear distinction between which types are mutable and which types are not. It comes up. And it comes up here, right? So we can't use, say, another dictionary or a set or a list as a key. We can use them in the values all we want of a dictionary, but they cannot be keys in a dictionary. The reason for this is that dictionary keys are hashed, and a hashing algorithm is a way of producing a unique result, a unique number, essentially, for a given value. If you change the value, you have to update the hash, which means you need a system of checking to see if the value has changed, right? And dictionaries are even though they seem bulky, they seem like they would be potentially slow and unoptimized. They are a very optimized type. And if you started adding features like that, you'd start losing some of the benefits and some of the nice things about dictionaries. So the simple answer is just, if you if you have a list and you really want to use it as a key in a dictionary, cast it as a tuple first, something like that. Okay, cool. We delimit dictionaries with curly brackets, and the syntax follows the curly brackets. Inside the curly brackets, key, colon, value, pair, comma, another key, colon, value, pair, comma, key, colon, value, comma, key, colon, value. Okay, cool. So that's our review. We're close to halfway. Let's just take a break right now, and we'll start in on breakouts when we come back. So let's reconvene at 4 minutes after the hour. Also, if you're just gonna sit around, if you have a question, feel free to pop it in Slack. I'm just gonna stand up and grab my water really quick, but I will answer any questions I see as soon as I come back. Just another reminder, if you don't, or if you finish early, just go ahead and post your code. Don't wait till I ask for that. Okay. There's that. Go ahead and post your code. I'm going to show a solution for this. Okay. As I was taking that question earlier, I thought this is deserving of the way I really wanted to answer this is actually deserving of a full solution. I think I explained the thing about input, but I want to emphasize good workflow habits for y'all. Part of that is these are non-ASCIIs, excuse me. Part of that is testing, in my opinion. Okay. Cool. So I'm gonna show a solution for this, and don't worry if you're not finished with your solution, go ahead and just paste what you have in. I'm going to show this solution not because I think y'all need help with the solution, but to show you how and why I go about solving a problem, like what things I do first, the order of things I do, the order I do things in, excuse me, and like where I do and don't put energy, particularly don't put energy, right? Like there's certain times where I'll look at something and I'll be like, I don't need to think this through. I can get Python to do the thinking for me, right? I bring that up specifically because I notice a lot of people who are new to coding, it's easy to come in and think like, okay, I've got to force my way through every problem with nothing but the grit of my own brain, and it's like, I won't ever discourage you from like taking it on to understand a problem, but a lot of getting good and getting to the point where you can be productive with coding is learning how to offload the difficult tasks onto the language as you're working, right? So, okay. So I'm going to read through this. I'm going to take a test-driven approach, and I'm going to try to put my energy where it matters, and we'll just kind of talk about that as I go. So it says write a function that prompts the user to input numbers separated by dashes. And presumably it means this space dash space pattern like this. We want to have this substring as part of the input. Like I said before, I'm just going to treat this as an input into the function via a parameter and an argument rather than an input from the input function that the user is going to put in via the terminal, right? So I'm going to just treat this as an argument instead of an input function. So your script will take those numbers and print a dictionary. Okay, so I'm already starting to get an idea. I have a couple pieces of information in my head, and I'm already starting to feel myself forget things. So I want to make my life as easy as possible. The couple of pieces of information I have is the structure for this input and the type of the output. So let's do this. I'm going to start, the very first thing I'm going to do is I'm going to start with my test. I don't know what to call the function yet, so I'm just going to give it a meaningless name. Oh, I can't tell if I spelled that right. Okay. My function takes in, or I'll call this imp for, I'll call it arg for argument. It takes in a dash separated number string. Okay, so let's do 3. Oh, 3. I say 3 and then I hit 4. Okay, space dash space. Okay, cool. It's way too much here. I got carried away. I like to keep my inputs small for testing things. That way I don't get some big jumble of output and have to like parse through it. I just want enough to see that what I'm doing is having some effect. And it looks like I have an example here, so I'll probably get rid of this in a second here. Okay, so your dictionary will take those numbers and print, or your script will take those numbers and print. Instead of print, I'm going to return because it's a best practice to always return. I'm going to return, and then this is going to print the return. We'll pass in my argument there. So notice I'm starting with the invocation. I'm starting with the place where I'm gonna use the function, and this keeps me obliged to write something that works like this, right? Like I'm setting the expectation for how I want this to work, and I haven't even started with the definition yet. So the script will take in those numbers, return a dictionary where the keys are the inputted numbers. Okay. So def my function takes in, I'll give it some other name, num string. Notice the name I give it describes basically its type, right? The type is a string, and specifically it's a string of numbers, and that's significant to the way I want to think about the type. And then we're going to return a dictionary. I assume every problem is an accumulator problem until I'm proven otherwise. Until I get into the logic and discover I don't need to use an accumulator for this. Right out of the gate, I'm just going to assume it's an accumulator pattern problem. So I'll create a target, an accumulator target, empty dictionary, and then just return that dictionary. So notice I have this pretty complete set of things. It doesn't do anything meaningful or important yet, but I can run it and it returns that dictionary. And as I work on my code and alter this, if at any point I'm confused and I wonder if what I did created the right result or created a desirable impact, got me closer to the result or further away, I can run it and I can monitor my result. I'm returning the dictionary, and then I'm printing off this function. This function expresses the value that I tell it to return. So this function expresses the dictionary, evaluates as that dictionary because I said to return it, and then we just print off whatever this function expresses, which is the dictionary. Okay, so this is the basis. This is the foundation of where I want to start solving my problem. I've got a little bit of everything. I've got the scaffolding in place. Now all I got to do is write this logic in the interior here, and it's, from here on out, it's just easy problem solving, and I don't have to do the thing of like, oh, I hope that did the right thing because, I don't have an input and I don't know what to expect, and I'm kind of guessing in the dark. Okay, so now let's look at the structure of this dictionary. So returns a dictionary where the keys are the inputted numbers. I can do that right now. For K, comma, V in D, in numster, let's say, what am I doing? So for num in numster, D sub num equals, and I don't know what the value is at this point. I'll just do 0 for now. So the keys are going to be the inputted numbers, and the values are going to be the squares of those numbers. I'll just keep it at 0 for now and just see what I got, right? So I look at my dictionary, and I certainly do have the inputted numbers, but I've also got spaces and dashes, and it's a bit of a mess. So I don't want the spaces and the dashes. I only want the inputted numbers. So right away, I can just say if num is not n, and I'll just make a list with a string that has a space in it and a string that has a dash in it. Then I can do that, and that'll get rid of spaces and dashes. That's one way to approach this. This is not so great, because what if I had a multi-digit number? Like, what if I had 73, right? Or let's do actually 75, right? So notice we're going to get 7 and 5 as different characters. So really what I want to do is split this into a list of numbers, or at least number characters, right? So this is a string, and I can string dot split, and I want to split on a substring of space dash space, just like that. And I'll just comment that out for now. When you're writing for loop, it's always good to kind of do some work and make sure your identifier that you create in the for loop, your variable thing, is what you want it to be, right? So what I want to see is only the numbers, and I want to see 75 as its own number, not 7 and then 5, right? So let's see, 3, 4, 75, 109, and I've got 3, 4, 75, 109. Good. So that gives me num. Okay. Always keep your types in mind. So if you're curious about the type, print it off really quick. These are strings. So we want these to be ints. So if I cast those as ints, let's just make sure I'll multiply them by 100. And multiplying them by 100 proves to me that they're going to be integers and not strings. If these were strings, we'd get a very different result. We can multiply a string, but it's not going to be, it's not going to be the same result, obviously. Okay, so this tells me that int num correctly casts num as an integer. So if I want that changed to stick, I can just say num equals int num, right? And then now I know num is an integer. So now let's test that out with just num. So you see how much I'm running my code? I'm getting errors. I'm guessing. I'm checking. I have this system down pat at this point, but like, this is, this problem is not challenging for me. But on problems that are challenging for me, it's the same process, but I get a lot more errors. Because that's like this is something that I've found to be true. At every stage of my growth as a programmer, I still get lots of errors. I still my code doesn't do what I intended it to do. I have to scratch my head back to the drawing board. And the thing that makes it quick is this sort of constant guessing and checking. So let's just kind of wrap this up a little bit. Well, we'll just get through this real quick. So I've got the integer version of my num. I'm going to say d sub num equals num squared. And then we're going to return d. I think that's it. I think that's all I wanted to do. Oh, num squared, just like that. Cool, that looks good. Okay, probably I could have finished reading the problem statement all the way beforehand, but so if I inputted the numbers 1, 5, 8, and 10, and let's actually try this out. This is perfect. So I've got these lines here, and I'll just paste in that test. So given that input, I want to see this as an output. And obviously, see, it comes out in a different order. Actually comes out in sorted order. So 1 and 1, 5 and 25, 5 and 25, 864, 864, 10 and 100, 10 and 100, right? So these are in a different order, but they are actually equivalent to each other. So that gives me the correct answer. Okay, cool. So you can do this too, and your process is probably going to look different than mine. But it's absolutely fine to just run the heck out of your code. Run it like you're trying to light your CPU on fire. You know, like there's if you ever ask yourself, like you're in the middle of a problem and you ever ask yourself, would Clark tell me to run my code at this point? The answer is yes. I would absolutely tell you to run your code at any point. Cool. So hopefully that's helpful going forward. Let's move on to another breakout. Yeah, let's do this one. Oops, I actually have this one right here. There we go. Okay. Let's wrap that one up there. I think that's a little short of the time. That's okay. Alright, if you're looking for a solution for this one, here's one right here. There we go. So I'll do a quick recap on this. So write a function that takes in a string. Are these the same? Okay, whatever. They're named differently. Write a function that takes in a string, return a dictionary where the keys represent unique characters in the string, and values represent the number of times that character appears in the string. S equals, this is our string, should really be part of the thing down there. I think we made a mistake here. These are different. Oh well. Word letter count. Yeah. Anyways, this first one just this first function just cleans the string, by which we mean it just eliminates all non-alpha characters and lower cases everything as well. So cool. Quick recap on the zip function. You know how to iterate over a single data structure, but what if you have parallel lists? How can we iterate over these at the same time? So here's our syntax for I and j, so for element 1 and element 2 in zip list 1, list 2. So if you ever find yourself asking the question, how do I iterate over 2 lists at the same time? Zip is your answer. We've got another breakout. There you go. All right, cool. Go ahead and get in your answers. Cool. All right, so as you can see, let me get my screen share. I should have mentioned this ahead of time, but when I was talking about tests before, I look at these and like this is all the information that I need to construct tests, right? So for this, I'll just copy these in here. Just grab, delete those real quick. All I need is just something to tell me what my for a given input, what I expect for the output. Oh, this isn't res. This is imp. Oops. Deleted the wrong part. Imp. So here's the imp. There's the expectation. And then we could do a result would be the result of the function. So I'll go through a quick solve on this. Write a function that takes a string of numbers separated by commas. Your script will take these numbers and store them in a list of tuples. 2 at a time. Use the zip function to do this. If the user inputs an odd number of numbers, then make the largest number of pairs possible. Okay. What should I call this? Like def tupulator. Tupulator to the return of the tuple. No, okay. That's too much. We'll just call it tupulator. Just thought it sounded like Terminator. Okay. Let's say the input is text. It's not just text. It's a num string. Again, we'll do numster. It's comma separated this time, but numster lets me know what it is. And this one we can kind of do, since we have zip, we can circumvent actually the need for a accumulator. But I'll do an accumulator solution first. Let's do this. So we've got, we'll say res equals. So I'm just writing my test a little differently this time, but it's still a test. We're going to take in imp, and we can print true or false is res is our result equal to our expectation. And then we'll print, oops, I don't need to print again. I don't need to print in the print. I'll just print out the rest so we can see the result afterwards. So we'll see true or false, and then we'll see the result of res. This is just another kind of structure that I'll use to build up tests. There's a lot of ways to do this. My point in showing you this is not to say like, hey, here's a structure that you have to memorize. It's like, do whatever you want, you know, whatever makes sense to you, just so long as you're calling the function and you have some expectation about what that should result in, right? It can be precise. These are precise. It should give me exactly this, you know, like let's say if I was going to analyze a huge document or something, I wouldn't necessarily go through and think out what each result should be if I was going to get like a giant dictionary out or something. But I would make some assertion. Usually I'll do it in a comment or something, just about what I expect. So a test just needs to include, like, for a given input, I expect some output, and you can lay it out however you please. Okay. So for this, I wanted to return. Looks like I want to return a list of tuples. So let's do the accumulator version. We'll do a list, and I'll return list. Oops. It's a list of tuples. I'll remind myself of that. I'll call it tuplist. So now I can say I'm just going to call it L and R for left and right in zip, and I'm just going to slice the string. I'm going to slice the string at sort of alternating positions. So I'll say numster sub colon in steps of 2, and we'll do this one starting at index 1 in steps of 2. So that's all I'm doing, right? So this one starts at index 0 and goes to the end in steps of 2. This one starts one index ahead of it, right? So this one's going to get all the even indices, and this one's going to get all the odd indices. And if we have an odd length in numster, then it's just going to go through as many pairs as it can, and then it's going to stop. So now I can just tup list dot append, and I'll append a tuple, so kind of double parentheses there, of L and R, and that should give me what I need. Oh, it sure didn't. Because you know what? I totally forgot that numster is a string. So what I need to do is convert it to a list. Let's call this numList equals numster dot split, and I actually want to split on commas, comma space, I believe. Yeah, comma and space is the delimiter that I want to split on. There's numList. Just ran it again, and I was like, wait, it didn't work. I forgot to replace numster with numList. Okay. Cool. So we're definitely a step in the right direction, but if you look, we're still getting false, so our tests are still failing. That's all right. Our tuples contain strings of the numbers. They're still strings, so I'm just going to cast these as ints right here. This will express an integer value of those digits, int, like that. And we get true and true, and we can see our output. Perfect. So this is I do really like doing things this way. You don't have to remember this pattern, but this sort of like see if res and exp are equal explicitly, you get a true and false, and then at least look at res, the result. Then that way I could see, when I was getting falses, I could see, oh, well, that needs to, I have strings there and I'm expecting integers, so you can kind of monitor things that way. Yeah. Cool. Oh, I said there was a non-comprehension solution too. The non-comprehension solution is, oops, we're going to cut this. We're going to, actually I'm going to do list of this. We don't even need that. We don't even need tuplist. We could keep this, or we could replace both instances with that, and then we can just do it on a line. Bingo. Nope. So I still have to do something to the find a way of converting the numbers. Oof. It's getting more involved. All right. Well, I'll leave that to you. Map will be your friend in that. If you want to take on that challenge, I want to just move on so we can get into some other things in the last little bit of time we have. Okay. If you want me to finish that problem after class, just let me know. Comprehensions. We could actually use comprehensions to solve this problem too. So comprehensions, at the beginning of class, well, near the beginning of class, I mentioned that we were going to cover some different kind of iterators, right? So again, I want to emphasize this. For and while are sort of your mainstay tools for problem solving for now. The reason is that they're expressive, they're powerful, they're good for a wide variety of things. Just like for loops are kind of a subset of while loops in terms of the problems that they can solve. Let me rephrase that. The problems that a for loop can solve are a subset of the problems that a while loop can solve. In other words, a while loop can solve anything a for loop can solve and more. So comprehensions are sort of a subset of for loops in terms of the problems that they can solve. So let's look at this. So imagine this is actually a really good problem to turn into a comprehension. It's not terribly complicated. Let me get back to it though. I'll come back to that in 1 second. Let's just write a really basic comprehension. So let's say I have a list, and I'm not even going to write this in a function. A list of numbers, 4, 3, 5, and then I have a squares list. Squares equals empty list, and I want to accumulate the squares. So I'll say for I n list squares dot append I squared. Print squares. Okay, so there's my squares of 4, 3, and 5. So I could turn this into a comprehension really easily. And we'll just do it in squares right here. The way a comprehension works is we tell it, we do it like this. Anytime you have a simple for loop like this, you can break out the thing where you're appending to a list. So a comprehension is sort of bound to a list. It's called a list comprehension. I should call it a list comprehension. So you'll take the thing that you're appending and you'll put that first. So I squared, and then you'll delete the append part and any junk around that. And then you'll put the for loop head after it and clean up the colon after the for loop head. So this says I squared for I in list, and this is a complete comprehension. Gives me the same thing, right? I don't even need to save it in a variable. I can just use it wherever I need it, just like that. It's pretty nice and easy. So this looks a little funky. It can make for some really elegant code. I would say if you're, if this looks intimidating at all, don't worry about it. Focus on for loops. That's where, it's more important to like develop skills with tools that are going to help you just solve problems rather than, using the perfect tools or whatever. So a little context here. If you go on Stack Exchange, the reason we teach this, if you go out into the world, out on the internet, and you ask questions or you look at solutions, you will see comprehensions used at every available opportunity. And it even says in the Python documentation, comprehensions are officially, it's canon in Python that comprehensions are officially the Pythonic iterator, and that they should be used wherever it's possible to use them. I kind of get why they did that, but I mean, I kind of don't like it quite, because what it results in is there's a lot of sort of complicated for loops that get sort of crammed into comprehensions, and this is a simple, elegant piece of code. Like if you know how to read this, this is just really nice. Very small, inline, evaluates to a list. Just really nice. So this takes a simple for loop and it makes it very elegant. And it takes a complicated for loop and makes it potentially an unbearable mess. So when your code gets complicated, it's much easier to deal with. It's much easier to read in for loops because things are broken into multiple lines. So it can get a little hairy out there. You might see some like really long, nasty comprehensions. So you don't have to use them, even if people tell you that you do have to use them, because people will. People will say, "Oh, you're not really a Python programmer until you're only using comprehensions." If anybody says that to you, they don't know what they're talking about. So eventually you will use them. I use them. I love them. They're great. But I use them kind of sparingly, and I use them only when my code won't suffer for doing it. So we don't have time to get into this, but we can use conditions inside of comprehensions. And the way that the logic around this shakes out is a little complicated. Sometimes you have to put the condition at the end, and sometimes you have to put it in the beginning. But yeah, suffice it to say, that's a comprehension in a nutshell. There are times when I think the big appeal of them is that people hear that they're faster. I've never optimized code. Code optimization is something that I explicitly don't focus on in this class. My goal is to get people to the point where they can like get to, like I keep saying, getting to working solutions. So that's really the goal. But I really like optimization problems. It's something that I really enjoy. I've never significantly improved the runtime of an algorithm by converting a for loop to a comprehension. I've like gotten a little bit of speed. You can get a little bit of speed out of a comprehension, but it's not a huge boost like some people think it is. So if anybody tells you it's more optimal, it can be. It often is, but it's often like a little faster, not like way faster or something. So use them sparingly. I'll leave it to you to go through the rest of this material. Sorry we didn't get through it all. DM me if you need any help and support. I've got enough free time in my schedule for other mentor meetings, so don't be a stranger. Awesome, cool. We'll wrap up there, and y'all have a great rest of your night. I'll see you, I think Saturday is my next class. Feel free to, let me stop the recording and everything, and we can take questions.